Hello, everyone, and welcome to today's lecture. We're going to talk about the BERT language model. So here are the learning outcomes for today's lecture. We're going to have 6 different passes over the BERT language model, and in each pass, we're going to get deeper and deeper into the technical details of this model. So in pass 1, the learning outcome is being able to describe large language models. In pass 2, we will learn about the input and output of the BERT language model and see an example in Python. Then in pass 3, we're going to specify several use cases of BERT. In pass 4, we're going to be able to explain the attention mechanism and its significance. In pass 5, we're going to recognize 3 innovations used in the architecture of transformers and BERT. And in pass 6, we're going to be able to explain the pre-training and fine-tuning of the BERT model. There's also a pass 7, which won't be recorded, and it's going to be left as an assignment for those of you who have a course with me. All right, so I would like to thank these individuals for sharing their material publicly. The slides I'm going to use contain material from all of these authors. So let's start with pass 1. So in pass 1, I'm going to explain large language models very generally. So large language models are a subset of deep learning. And you already know that deep learning is a subset of machine learning, and machine learning is a subset of AI. So these large language models are general purpose models that can be pre-trained and fine-tuned for specific purposes. So there are 3 key features in this definition. First of all, they are large, meaning that the training data is large in the order of petabytes. And also these models have large number of parameters, like billions of parameters. And these parameters allow the model to learn, language and gain some general understanding of the language. The second feature of this definition is that these models are general purpose. So unlike traditional approaches in machine learning, where for each specific task we build a specific model, these large language models are not designed just for solving one task. They are general purpose, meaning that because of the commonality of human language, they are developed in a way that they can gain some general understanding of language and then use for a number of different language-related tasks. And these models are pre-trained and fine-tuned. So by pre-training, essentially we're referring to the process in which these models gain that general understanding of language from a very large data set. And then by fine-tuning, we're referring to the second step of development of these models, where they are fine-tuned for a specific aim with a much smaller data set. So the BERT model that we're going to discuss today paved the way for the generative AI revolution. All right, so here are some common language tasks. For example, text classification is a classic example where we have text as data, and we want to classify, let's say, different sentences into positive and negative classes. This is called sentiment analysis. Another common language task is question answering, where an AI model is used to specify answers to a given question. Document summarization, I think, is quite self-explanatory, and text generation is another common language task. So these large language models solve many of these language problems that you see. So some of the benefits of these large language models over, earlier methods in machine learning. Um, um, so some of these benefits are uh, the fact that a single model can be used for different tasks. For example, um, a single large language model can be used for translation, sentence completion, text classification, and question answering. Another benefit of these large language models over earlier, task-specific approaches is that these large language models require rather minimal field training in order to show some decent performance. So they only require some little domain-specific training, and this allows these models to do few-shot or zero-shot learning. So by few-shot learning, we refer to the cases where these models have only seen a few cases relevant to the domain that they are being used in. And in zero-shot learning, essentially the foundational language model is capable of providing, relevant predictions or relevant, handling tasks in a meaningful way without being trained with domain-specific training data. So the performance of these models are continuously improving as more data and more parameters are added to them. And these days, the largest, large language models that we know are so large that only very few companies in the world, very few organizations have the computational resources to develop them. So what you see on this slide is a recent history of language modeling. So you can see the gray part where, in 2014, methods like RNN and LSTM were state-of-the-art methods for language tasks like translation. So these were methods that could incorporate the order of the words in the sentence. But they were still, rather basic in terms of incorporating the context of the, you know, uh, words as they were, processing the input. For example, you can consider the two homonyms of the word bank. So bank river and bank robber. Of course, they mean different things, but if we do not incorporate the context of how the word bank is used in a sentence, we cannot distinguish between them. But then in 2015, attention mechanism was introduced. So attention mechanism allowed researchers to develop methods where the context of the words in a sentence were incorporated in a more efficient and a more suitable way. So attention mechanism kind of paved the way for the development of transformers, and transformers are, an architecture that is made up of an encoder and a decoder, and then the BERT model is an encoder-only architecture, which is based on a transformer architecture. So, but this video is being recorded in March 2024, and by the time that you're watching this recording, you know that there are many models more advanced than the BERT model. But as the timing of the recording of this video, I only know about T4, GPT-3, Llama 2, and Gemma. So these are models that are called open models. So they are not necessarily open source based on the definition of the open source foundation. But for example, Llama 2 from Meta AI and Gemma, which was introduced by Google just 2 weeks ago in February 2024, these are models that are open in the sense that people can download them and build on top of them to solve their own specific language tasks. All right. So this was pass one. Um, Now in pass two, we're going to get deeper into the technical details and learn about the input and output of the BERT model. So you can imagine that the BERT model is a machine that takes text as input. For example, it takes this sentence as input, and it returns um, vector a bunch of vectors for this input. So if the input is everybody dance now, it's going to return a vector for the word everybody. It's going to return another vector for the word dance, another vector for the word now. And then there are also two special tokens, CLS and SEP, um, and the BERT model also produces vectors for these two special tokens as well. And we're going to talk more about these special tokens later when we talk about the pre-training and fine-tuning of the BERT model. But for now, you can imagine that the vector representation for CLS can be used um, as a vector representation for the whole sentence input. So you can imagine that if you want to do sentiment analysis on sentiment classification, essentially on the input sentence everybody dance now, this vector would be useful for sentiment analysis. So here is an example of the BERT model in Python, as a very specific version of BERT that I'm going to load from TensorFlow Hub. So this Python code if you run it, you will get the same results. If you run it on a normal, ordinary computer or on Google Colab, it should work as you see. So first, I'm going to load BERT's preprocessor from here, and then I'm going to load BERT encoder from this address, and then I'm going to define a function that takes a sentence as input, then that input goes through the preprocessor, and then the preprocessed input goes through the encoder, and then I return the main output of BERT, which would be a dictionary, and in that dictionary there will be a pulled output, which is the key referring to the CLS classification from BERT. And now if I give a sentence to this function, it's going to return the CLS vector representation for my input. So here is an example where I'm giving this sentence to BERT, to my function, and for the sentence $500 discount, hurry up, I'm going to get this vector representation. For another input, hi prof, will the exam be easy? I'm going to get this vector representation. Now, if I want to build the email spam classifier, these two vectors will be useful. So for that, I need a label data set that I can put, on top of the BERT model that you see on this slide. So this is how the BERT model can be used, and this was pass two. All right, now in pass three, we're going to get a bit more technical on the details of the BERT language model and learn about the attention mechanism. So if I Google this question, who is Margaret Atwood, I'm going to get these results. And on the result that I get, I see that first I get list of websites that are relevant to my question. Then I see that there's a summary related to the search query that I had provided. And I also see that on my desktop, when I search who is Margaret Atwood, I'm going to also get some, parts of the, result that is shown in boldface font, or they are highlighted. So from all these three parts of the Google search results, which ones do you think are impacted by the BERT model? So do you think BERT is responsible for feature number 1 on this slide? Do you think BERT is responsible for 2? What about 3? So I'm going to give you some time to guess. All right, I hope you have guessed already. And I guess I can say that most of you answered correctly, because BERT is responsible for all 3 of these. So BERT does text encoding, which allows Google search to get this, relevant output, this relevant website, even if there's a misspelling in the search query that I provided. So even if I had misspelled the word Margaret, I would have got relevant results. And this is because Google search uses the encoding of my search query. Also, BERT is helpful for similarity retrieval. So, and that's another reason why Google search works. So it is retrieving, websites whose vector representation is close to the vector representation of my query. Also, BERT helps with text summarization. So this summary that you see in here actually doesn't exist like this on Wikipedia, but based on my query, which was a question, BERT has summarized a paragraph on Wikipedia, and in this summary, you can see that, for example, the birth date of Margaret Atwood is not mentioned. This is because for answering my question, or for summarizing text related to my question, the birth date is not needed, because it was about who is Margaret Atwood. And in item 3, BERT is helping with question answering. So it is essentially finding some parts of the some part of the return text that could be viable answers to my question. So my question was, who is Margaret Atwood? A potential answer is a founder of the Griffin Poetry Prize. Another answer is a varied and prolific writer. Another answer is a poet, novelist, writer, essayist, and environmental activist. So this shows 3 examples of use cases of BERT, especially in the context of Google search. And this was inspired by a video from Alammar. So here is another example. If you have used Gmail, you have already seen BERT in action. So you can see that sometimes on Gmail, we get these, suggested responses. So this is another use case of BERT that is called response selection. All right, so this was pass 3. And in pass 4, we're going to get even deeper into the technical details of the BERT language model. And for that, we start with the attention mechanism. All right, so now we're going to talk about the attention mechanism and its significance in language modeling. So attention mechanism was used in the transformer architecture, and transformers were fundamental to the development of the BERT language model. So in order to understand what attention mechanism does, let's go over this simple example. So before BERT model was introduced, which uses attention mechanism, if someone searches for parking on a hill with no curb, they would get this result. They would get result, which is, as you can see, about parking on a hill that has a curb. So of course, this is, a failure of Google search if this was the case. But after the BERT model was introduced, Google search will pay attention also to the word no. And because of paying attention to the word no, it can correctly understand the search query, and it's going to provide results that are specifically about parking uphill or downhill where there is no curb, for which the method of parking is quite different. So this is because before the attention mechanism, the way that this search query was processed was that the word no, as it is a common word in English language, would not receive, sufficient attention, and Google would return result for which parking is mentioned, hill is mentioned, and curve is mentioned. And you can see that in this kind of failed response, we have curb, hill, and parking. So based on that very naive way of processing text input, it was, doing the job that it was supposed to do, returning result based on, matching keywords. But now you can see that after the BERT language model, Google search is capable of recognizing how fundamental the word no is to processing this input correctly, and it's going to give us results that are specifically about parking uphill or downhill where there is no curb. So language is probably the most fascinating innovation of humankind, and the one reason why it is so fascinating is that it is both limited and limitless. So in the words of my favorite contemporary poet and philosopher, words in finite chains, yet boundless realms they unveil. And this is, of course, from ChatGPT. So Google receives 8.5 billion search queries every day. And you might be wondering what percentage of these search queries are totally new questions. So I'm going to give you a few seconds to make a guess. So any number between 0% and 100%. All right, so actually 15% of the queries that Google search receives are totally new. And this is a reason why search is not a solved problem. And BERT has been very fundamental in improving Google search. And for this, I have another quote for you, this time not from an AI chatbot, but from Pandu Nayak, who was VP of search at Google. And according to him, or according to an article he wrote at the time of development of BERT in 2018, he said BERT has been one of the biggest leaps forward in the history of search. So hopefully this allows us to understand the significance of the BERT language model. All right, so this was pass 4. Now we're going to move on to pass 5. And in pass 5, we're going to learn about 2 other fundamental innovations used in the architecture of transformers and in the BERT language model. All right, so now in pass 5, we're going to talk about self-attention and positional encoding. So a transformer is an architecture that is made up of an encoder and a decoder. For most people who want to learn about transformers for the first time, at some point they will see this figure, this schematic representation of architecture of a transformer. And this is from the paper, Attention is All You Need. For a figure in a scientific paper. It is an excellent, detailed technical figure. But for the purpose that it is, trying to serve these days when people try to learn about transformers, I think this is not the ideal figure because there are just so many colors and there are things that are connected to each other in a certain way, and there are a lot of technical jargon. So at least in my case, when I saw this figure for the first time, the impression I got was kind of, sort of giving up on learning what transformers are. But I hope that you don't get that impression because I'm here and I can help you understand the key technical details of that are relevant to understanding the BERT language model. So first of all, I should tell you that this architecture represents two parts. So here we have the encoder part, and here we have the decoder part. And we are in luck today because the BERT language model is an encoder-only architecture, and we can forget about the decoder part of what you see on this slide. So we can simply forget about the decoder part for now and just focus on the encoder part. So the role of the encoder is understanding what language is or what is context. And the developers of the BERT language model stacked 12 encoder units on top of each other and called it BERT base. They also produced another version, BERT large, which had 24 encoder units stacked on top of each other. And the reason why they used multiple encoders on top of each other is the same reason why we use multiple layers with a nonlinear activation to increase the expressive power of deep learning models. So for the same reason that we may need, deep neural networks for handling certain tasks, here also for language modeling, they needed to include multiple encoders. So they went with 12 and they went with 24 for BERT base and BERT large. So the working definition now we have for BERT is that it is a stack of encoders. Later, we're going to make this definition a bit more precise by including the subtitle that it is a stack of encoders with clever pre-training and fine-tuning. But for now, you can just imagine that BERT is a stack of encoders. It takes as input, then it does some embedding. It represents, words or tokens in the input as vectors. Then there's a positional encoding part. And after that, what we have is essentially tokens of the input that are represented as positionally encoded vectors. And they enter, an encoder, which, does some, processing on the input. And in that processing, we have multi-head attention, which we're going to discuss later. And eventually what we get as the final output from BERT would be a vector representation for every single token in the input, just like what we saw earlier in pass 2. So I told you about how attention was used in the transformer architecture and how transformers were fundamental in the development of BERT. But this was sort of a simplification because there are also two other fundamental innovations which were used in transformers and in the BERT language model. So let's start with positional encoding. So let's look at this sentence, Alice dumped Bob. So Alice and Bob are, names I've used for hiding the identity of two of my friends who used to be together. And if you talk to Alice, she will tell you that the order of the words matters a lot in this sentence. So it was Alice who dumped Bob, not the other way around. So in order to process this input properly, we should incorporate the order of the words in the sentence. And positional encoding is a very, intuitive idea for incorporating the order of words in the input. So what we're going to do is attaching indices representing, the position of the words in the input in the sentence, and um, when we try to represent Alice as a vector, it wouldn't be just a vector representing the word Alice, but it would be a vector that represents both the semantic meaning of Alice and the position of this word in the sentence, which is position 1. So what we're going to do is using a vector that represents Alice, another vector that represents position 1, add them together, and the result would be a vector that represents both the semantic, um, you know, representation of this specific word and the fact that this word has appeared in the first position in this sentence. So this is called positional encoding. All right. Let's now see the attention mechanism. Of course, we have seen it earlier in the previous path when we talked about this example of parking on a hill with no curb. So if you haven't watched that part, maybe you can go back to the previous path when we were talking about attention mechanism and see how attention mechanism allows Google search to pay, sufficient attention to the word no when it is processing this input. All right, and self-attention. So here is an example about self-attention. You can see that for this input, if we want to process it correctly, we need to, or the model needs to figure out whether the word it refers to oven or the word it refers to pizza. And for figuring out this correctly, it's going to incorporate some information from every other word in the sentence when it is embedding the word it. So this is called self-attention. So what we've done in here is allowing the model to incorporate some information about every other word in the sentence when it is processing the word it. So when it is when the model is processing the word it, there will be some information that will be added from every other word in the input, and through in the pre-training part, based on the backpropagation, it's going to learn that for processing this input properly, to have a low loss in the objective function, it will learn that it should pay more attention to the word pizza rather than the attention that it should give to the word oven. And this is because there's another word in the sentence, taste, and it does make sense to say pizza tasted good, but it doesn't make sense to say oven tasted good, right? So as the BERT language model is pre-trained on the whole Wikipedia corpus and all Google Books text, it has seen many examples containing words pizza, oven, and taste. And just based on this statistical associations between these words, it has gained this understanding that it is much more likely for it to refer to pizza in this sentence rather than it referring to oven. And this is called self-attention. So now, with positional encoding, attention, and self-attention, these fundamental innovations were used in transformers and allowed transformers to revolutionize language modeling. And then 1 year after the development of transformers in 2017, we had the BERT language model, I guess, in 2018, which at least at that time was the most sophisticated, the most capable language model for a number of language tasks. So this was pass 5. All right, now we're going to talk about the pre-training and fine-tuning of the BERT language model in pass 6. So there were 2 different objectives used in the pre-training of the BERT language model. So you can see that the input was, if the input is something like this, so my dog is cute, he is fluffy, and the input also has these special tokens like CLS and SEP that we saw earlier. The input goes up in let's say 12 layers of encoders, and then what we get in the end will be some vector representation, vector representations corresponding to each token of the input. And based on these vector representations, there were 2 different objectives that were used for calculating the loss and kind of operationalizing the pre-training of BERT. Objective 1 was only based on this vector, the vector representation for CLS, which we saw a bit earlier in Python and in pass 2, I believe. So objective 1 is called next sentence prediction. And for objective 1, as I said, we only focus on this vector. Objective 2 is masked language modeling, and for that, we use vectors other than the very first vector. So you can imagine for now that all these other vectors, let me just use a different color. You can imagine that all these other vectors are potentially relevant for objective 2 of pre-training BERT. So in the pre-training, BERT is simultaneously trained for both the NSP objective and the MLM objective. But before we come to the details of these 2 objectives, let's first look at the input of the BERT model for its pre-training. So this is an example of the input of BERT model. So as input, it receives pairs of sentences. So instead of just 1 sentence, the pre-training input were in pairs. So here is an example, and you can see that segment A of this pair is my dog is very cute, and segment B is another sentence. So segments roughly correspond to sentences, and tokens roughly correspond to words. And what you see in here is that the training pairs which were used in the pre-training of BERT were either consecutive sentences or a pair of sentences which were randomly put next to each other. So half of them followed each other in a logical, meaningful way, and in other half were just 2 sentences which didn't make sense after each other. And this will be used in next sentence prediction. And then another important thing about the input is that there are some special tokens. So CLS is the special token which will later be used for this classification task of next sentence prediction. But there's also special token for separator, that's SEP. This represents, the separators between different segments. And here you see another special token mask. This is because for the second objective, 15% of the words were masked. And in the second objective, BERT tries to, make predictions for words that are like for the word that is most likely to be relevant to fill in the blank. So here is now objective one of the BERT. So in objective one, we want to predict the next sentence. So it receives a pair of sentences. For example, the input could be something like this. The man went to masked word store. He bought a gallon masked word milk. Well, first of all, for us, it's easy to kind of predict that this input must have been something like the man went to the store, he bought a gallon of milk. So for us, of course, it's easy to predict the masked word, just like, a fill in the blank task. But anyways, BERT receives this input, and now that we're focused on the NSP task, there is a label corresponding to this input, the label that these two sentences are consecutive. And this label, this is essentially a binary classification task, and this kind of the name used for this class is next. Here is another example. The man went to masked word store. Penguin, masked word are flightless birds. So you can see that for this second pair of input, for this second input, which is another pair of two sentences or two segments, they don't follow each other logically. So it doesn't make sense to talk about a man going to a store and then talk about penguins all of a sudden, right? So the label corresponding to this input is not next. So this is a binary classification task. And based on the CLS vector output of BERT, in the pre-training phase, BERT is, essentially learning to predict whether two sentences follow each other or not. And this allows BERT to understand by directional context beyond, one sentence. So it learns the context across different sentences based on the NSP objective. So here is the second objective, the MLM objective. So for the MLM objective, BERT is used to predict the masked word. So as I said, something around 15% of the input tokens were masked. You can imagine that for input that is I, masked word a cat, BERT is used to predict the most likely word that fills in the blank. And if it predicts a word like saw or another verb that makes sense, then it will be essentially the loss corresponding to that prediction will be low. But if it predicts the word laptop for this input, the loss will be high. This is because the vector representation of saw and laptop are so much different from each other. But for example, if it predicts the word, let's say C, as the vector representation for C and saw are close to each other, or they have a high cosine similarity, making a prediction, predicting the word C in this example would also lead to a low loss. But of course, the lowest loss, the lowest error that BERT can have would be for predicting the masked word exactly correctly. All right, now if we put these two objectives together and also include the pre-processing that is needed for BERT in terms of positional encoding and the fact that input of BERT is made up of a pair of sentences, then we see something like this. So the input is like, my masked word is cute, he is very fluffy. So I guess for us, it's easy to predict that this could be cat or dog, right? Or some some pets, right? Um, so the input goes in the pre-processing part, essentially. In the pre-processing, each of these words is represented as a token. Sorry, is represented as a vector using token embedding. And for the token embedding in BERT, they use the word piece embedding, which is based on a vocabulary of 30,000 words, right? So in the word piece embedding, the word my corresponds to a certain vector. The word cute corresponds to another vector. So that's where, let's say, these vectors come from. But these vectors don't represent the context of the words yet. That's why we also have segment embedding. So all these vectors in yellow correspond to segment A, and they are the same vector. And all these purple vectors, again, are the same, and they represent segment B. So these will be added to the token embedding. And then we also have the positional encoding, right? So for positional encoding, they use the position embedding that essentially represents, the position of the word. So they represent 1, 2, 3, 4, and so on. But you may read more on the technical details of how they represented 0, 1, 2, and so on. So you will also learn more about that in PAS 7. All right, now that we have words that are we have vectors that represent the semantic meaning of each token, its position in the sentence, and the segment that it belongs to. Now the input goes to the first layer of the encoder of a transformer, and then another layer. So let's say that here we have 12 layers of encoders, and eventually there will be some, vectors that are, output from this model. So there will be a vector here for the CLS token, a vector here, which is the output corresponding to my, another vector corresponding to the masked word, and so on. So this is just like the vectors we saw for the example of Everybody Dance Now in PAS 2. So as I said, the very first vector will be used for next sentence prediction, and all these other vectors are used for masked language modeling. All right, so but what is the pre-train? What is the loss function for the pre-training? So for the pre-training, you can imagine that the length of these vectors that are input by BERT is not necessarily length of the vocabulary. In particular, the length of the vectors in BERT base was 768. And this was, just based on the design choices of BERT base. Otherwise, 768 is just the midpoint between 2 to the power of 9 and 2 to the power of 10. So it is, common to use a power of 2 as size of embedding. And in case of BERT base, they wanted a value something between 512 and 1024. And 768 is the, size of, essentially the length of each of these vectors. So each vector is a vector of 768 coordinates. But the size of the vocabulary is 30,000 words. So first we need a fully connected layer that, takes each of these vectors of 768 and process them such that the corresponding output becomes a vector with 30,000 coordinates, right? So now that we have that vector whose length matches with the number of words in the vocabulary, now we can calculate the loss. So let's imagine that this vector has 30,000 coordinates. Just for simplicity, I've shown a vector with 3 coordinates, right? So in this vector, we have some real numbers, right? So let's say the numbers we have are 1, -3, and 5, right? If these are the numbers, we cannot interpret these as probabilities. So we use a softmax function to convert this into a vector of 3 other coordinates, where those coordinates kind of follow the same order, and they will be values between 0 and 1, um, such that they add up to 1, right? So that's the purpose of softmax function. So this vector, when we apply softmax to it, so the softmax of 1, -3, 5 becomes this. It will be e to the power of 1, e to the power of -3, e to the power of 5, divided by sum of these 3. So the result would be, let's say, I guess e to the power of 5 is 2.7 to the power of 5, right? So it would be like 40, 50 something. When we divide it by this total, this will be the largest value. So it would be, let's say, 0.98. E to the power of -3 is very small, so this will be 0.0001, something like that. And e to the power of 1, 2.7 divided by 50 something or 60 something, it would be like 1%, something around that. But these calculations are not, um, that precise. But hopefully you get what I mean by converting this vector into another vector such that the order remains the same. So -3 used to be the smallest, and now this one that corresponds to -3 is the smallest. And 5 was the largest, and now this one that corresponds to 5 is the largest, right? And then we use a cross entropy loss. So this is essentially the something that we can interpret as a prediction. So this is something like y hat, and if the target y is 0, 0, 1, then cross entropy loss would be minus log of 0.98, which will be a very small number, right? Something like this. So this is the case of a good prediction. If we were looking for kind of, let's say, classifying into this word of the vocabulary based on this target, right? The target represents the ground truth. Here we have a prediction that corresponds to a very, very, very small loss. And this would be, a good prediction. And as the prediction has a low loss, the gradient will be small, and in the backpropagation, the weights will not change that much, right? But of course, in the backpropagation, it is based on, all the predictions in that batch, if we're doing it in a mini batch, for example. All right, so I think I've already provided a lot of technical details. So you can imagine that the pre-training loss is based on a softmax layer to convert these vectors from 768 to 30,000. This is a fully connected layer. And then at the end, there's a softmax activation function, which is used to convert real values into numbers between 0 and 1. And then cross entropy loss is used on the target and the result of softmax. All right, so we covered the pre-training. Now for the fine-tuning, the developers of BERT used the pre-trained BERT for different language tasks. One of the tasks that they used BERT for was single sentence classification. So let's say that here we have the BERT model that is already pre-trained. So we have done the process of mm, giving these pairs of sentences. Um, and now we have a foundational model that has a general understanding of language and context, but it still doesn't, solve a specific language task. Now with fine-tuning, we're kind of preparing it for that, for, a given task. So here we're preparing it to become, a classifier for single sentence input. So for single sentence classification, what they did was they essentially attached the fully connected layer here, and then they just used this vector representation of CLS for binary classification. Um, and I mean, it's not necessarily binary classification, but you can imagine that for the case of an email spam detector or sentiment analysis, this could very well be just a simple binary classification. So here we can attach just the fully connected layer, and do binary classification. And they showed that for some benchmark language tasks, such as binary sentiment classification on SST2 dataset, and on another classification task based on the corpus of linguistic acceptability, BERT model, had decent performance. So you can also imagine that the vectors we had in pass 2 in the Python code could be used for training an email spam classifier, right? So the vector representation we had for $500 discount hurry up was very different from the vector representation for the other sentence or other email body, which was hi prof, will the exam be easy, right? So if we have label data on text and uh, you know annotated labels correspond showing whether each input is spam or ham, we can use BERT to get those vectors and then use those vectors as features to build a binary classifier. All right, so this is the fine tuning of BERT.